Bismillah Rahman Rahim. Today we have our next video lecture, that is regarding UML state model, which is obviously the part of the series which we have already started, that is object oriented software development or object oriented software engineering. So we'll try to discuss the importance of UML state model in object oriented analysis and design, and we will see where we can use that state model diagram and what are the important ingredients of a state model diagram, and how we capture those transition and how that information is being used whenever we design the class definition. So here in the state machine diagram, which illustrates the interesting events and states of an object and the behavior of an object in reaction to an event. So the state transition diagram basically captures all important, interesting, noteworthy events, important events, relevant events. We can say all those events in which the object has to respond. All those events have to be captured where we need a response. The response might be different in different events, and in some cases in multiple events there will be a same response. So we will discuss the definition of an event, what type of events are there. We'll also discuss here about states of an object, because it is very important to determine the state of the object. And whenever we have the object definition, wherever we say that object has identity, object has certain attributes, object has, there we, it is also a part of the definition that object also have states, and all those states of the object basically determines what the values they have. So in different state, object can behave differently. So the capturing of an event, which is we call the noteworthy occurrence, it means the important occurrence or significance occurrence is considered as an event in our mini world. For example, if we talk about a telephone call, so we can say telephone receiver taken off the hook. That is something which happens, and if this happens, which state we are and how the state will be changed. For example, there when it is on the hook, the dialing tone was off, and when we receiver taken off hook, then the dialing tone is on. So there are events which are there. For example, in ATM machine there are certain events. For example, if we go for a cash withdrawal, so if we go for the cash withdrawal, the event happens and the ATM machine has to respond. The ATM machine has to validate the user and the card, and obviously the ATM has to respond according to the given event. Similarly, we talk about state, the condition of an object at a moment in time. It means the object states are there, and object usually changes states whenever there is a certain event. So we can say that event actually triggers the object to change the state. For example, very simple, start with a very simple example. So if we have, there is a switch, so when we on the switch, or there is a state when we call it the switch is off. So obviously my action will make the switch on and my action will make the switch off. So it means some event happens, and according to that event, that switch actually changes the state. The ATM machine is in ideal state, doing nothing, maybe presenting an ad, or maybe a message, and waiting for an individual to interact with the machine with a certain event which has to be responded. Transition is the third important aspect which we cover here in the state model diagram, that is the relationship between two states. So whenever there is an event and there is a response, so it is quite possible the object changes states from one state to another. So there are two possibilities: whether that event whether an event happens but there is no transition. So in that case you can see you can say that the object remains in the same state, or otherwise the object will change the state. Okay, and that is called a transition. So there may be multiple transitions, there may be parallel transitions, there may be conditional transitions, so on and so forth, which we'll try to cover in our model. A state transition diagram is a technique to depict the states of an entity, which is very important for us because later on that entity will be captured in our class model, which is our detailed design. So there we exactly know what are the states, and those states will be represented in our model. Secondly, the transitions of states of the entity. So we should know about the transitions, in which cases the state has to be changed. And obviously, if that state does not change, it means that there is something wrong. So it means we have to look for those events, we have to look for those operations, we have to look for those calls, and then we can correct it, because the transition of states, if it is defined in our mini world, has to be followed actually in our program or in a software. So the transition is another important aspect which we want to cover in this model. The trigger or the event, something happens that is considered as event. So happening of some event that caused the transition of state of the entity. So we have to capture all those events. So during requirement analysis, we are looking for those events, all possible events, where our system or software or a program has to respond, or a machine has to respond. So obviously that is part of our scope as well. That also defines our scope. The entity may be a physical device such as a light switch or a vending machine. That can be an entity as well. In a vending machine, we are looking for a particular drink, so we have to go through with the process, and obviously whenever we put some money into it or a card into a vending machine, the vending machine starts the process, changes the states from the ideal state, and then the next process is maybe looking for a particular option for selection, and obviously the payment and return back of money as well, along with the specified drink. It can be any other software physical device as well. All those physical devices which are normally used, which are actually classified as home appliances, are also physical devices. For example, we might be talking about a washing machine, we might be talking about an oven, or any other device, maybe a multimedia device. So entity may be any physical device, such as simple as light switch or vending machine. It may be a software system or a component. So it can be a software, not the device. So whenever we talk about a device, it means we are talking about an embedded application. So here it may be a part of a software application or a program. For example, a word processor or an operating system to respond in a certain situation. So there may be different commands as far as operating system is concerned. So how that operating system need to respond on those events. It may be a biological system or any other kind of system. Maybe we're talking about a cell or a human or any other biological system. So all these systems, whether they are physical, whether they are non-physical, or obviously we are talking about software components, remember that there are states, there are events, and there are transitions as well. And all these things are very important while we design our systems. So events can be further classified into various types. One type is called the signal event, as you see on the screen, the physical event. A signal event is the event of sending or receiving a signal. What a signal is, normally whenever we talk about a signal in communication, it means it is some sort of one-way traffic where an object initiates a signal to another object or a call to another object. Usually we are more concerned about receipt of a signal because it causes effects in the receiving object. So if we are interested in receiving of that signal, and obviously if that signal cause some effect in the receiving object, then it is noteworthy and it is important, and then it is regarded as signal event. So every signal transmission is a unique occurrence, but we group them into a single class. So in our model, what we can do is that we can put all those occurrences, obviously they have certain similarities, into a signal class and give each signal class a name to indicate common structure and behavior. Here you can see in this example that there is a flight departure and there are certain attributes, and that is classified as a signal class. So here we have airline, flight number, city and date. So it means a certain flight is departed from a certain airport, maybe a flight number this departed from Quaid-e-Azam International Airport at this particular time and date. So this is a sort of a signal which has been generated. Similarly, we might have a mouse button pushed class as a signal, so on and so forth. A second type of event which normally we deal with is called a change event. A change event is an event that is caused by the satisfaction of a Boolean expression. So it means that we're talking about a certain condition. We're talking about Boolean expression, so we're talking about a certain condition which activates when maybe it is true or stops when it is false. So it is based on true and false scenario. The intent of a change event is that the expression is continually tested whenever the expression changes from false to true. The event happens. So it means if that whenever that logical condition fails, that event might happen. For example, when room temperature is less than heating, set the point. When room temperature greater than cooling, set point. When battery power is less than lower limit, okay, change the condition. For example, in our devices, if we have a certain battery power, it automatically make our system or make our physical device to low power range so that you can effectively use it. When tire pressure is less than the minimum pressure, again all these conditions are Boolean conditions, and the event will not happen until that condition fails, and in that scenario the state will be changed. The third important type of event is a temporal event, and a temporal event is also called a time-based event. A time-based event is an event caused by the occurrence of an absolute time or the elapse of a time interval. For example, we are having various transactions, and for example at 2 p.m. Whatever the transactions we have, we execute or update those transactions. So in this case, we are not dealing with every single transaction actually, and what is happening, that we have a certain time point. So we can have a time point, for example, when date is equal to January 1, 2000. So it means here we are focusing on a particular date or a particular time, and we might have an interval. After that interval, that event will happen. So it's up to us whether we can have a time constraint or temporal constraint in terms of time points or in terms of intervals. The software view, which is very important for us because we are talking about object-oriented software development. So our focus basically is on the software side. The software view, the end product of a software is a program which executes. It means we're talking about an application, program, or a code which runs. In depicting the program, we can consider number one, variables. In depicting the program, we can consider variables which take different values, and we all know that what we do is that we actually the variables correspond to our objects, and the variable obviously instantiate with different values, and that is how we capture the state of an object. Secondly, the control structure and assignment states events in the program that change the values of the variables. So what are those control structures? What are those conditions? What are those statements, or what are those events which actually change the values of the variable, where object interacts with the other objects as well, communicates with the other object, changes the states as well. So that is basically the concept of software view. A very simple example to start with, just to have a little concept, and that example is about light switch. So very simple, we do not take too much time here. You can easily understand what is happening right now. There are two objects, one is switch, one is light. So you see what is happening. So if it is on, what you can do is you can turn off. So on, you can make it off, and if it is off, you can make it on. So obviously you cannot make off state to off or on to on, because it is already there. And so this is one representation, but this representation, as you remember, we have already discussed in the form of sequence diagram. And here, that the same representation in this on this side, you can see it is on the form of the table that is called a state transition table. So we have from state light on, what is the event, that is turn off, and where we have reached, that is off state. From here we start with the off, turn on, and similarly we reach to on state. So here we can build the state transition table. So as obviously if you have more states, more transitions or different events, so obviously that table will be complex. In number 3 you can see the same thing is represented in the form of state transition diagram, where you can see the light on is one state, and turn off, make it to the light off, and from here turn on, make it to the light on. Very, very simple, without any condition, without any controls, without any specified criteria. Very, very simple transition. But whenever we are capturing those transitions, there might be some conditions or transition actions which are also important to capture. There is also the concept of guards, means we can have multiple conditions as well. Transition can cause an action to fire. In software implementation, a method of the class of the state machine is invoked. So if something happens, so in a design perspective, actually that operation or a method call is there, which is obviously a part of a certain class. So it means a transition may have a conditional guard, and that condition, if that condition is true, then that transition will happen. If that condition is false, that transition will not happen. A very simple example, for example, if you want to have an amount using an ATM machine, if you enter the amount and that amount is let's assume that amount is less than the balance amount in your account, then obviously that transaction will fail. That transaction will not execute, or that transition may not be done. So there you have to terminate your transition, or you have to put an amount which is less than equal to the amount which is there in your balance. So that is conditional, because if we do not invoke conditions, the system might go into states where there will be no response. So obviously from the design perspective, that is not a good idea. So we have to plan our system in such a manner that we have to capture all the events, all those events which are important, relevant in the given mini world. Another important aspect in case of states, that you might have a nested state as well. And nesting, the concept of nesting means a state within the state. A state may be represented as nested substates. So we have a state, for example, we talked about light switched on. So light switched on is a state, but in that switch on state, we might have different functions which we can perform on the light as well. So in UML, substates are also shown by nesting them into a superstate box. So there we have a big box, the superstate, and all those substate will come inside into that box. A substate inherits the transition of its superstate. Whatever the transition the superstate carries, all the substates have to carry all those transitions as well. Allows succinct state machine diagrams as well. So the example here, you can see the guard and the condition is also there, and the nesting is also there. This box you can see here that basically represents the concept of nesting. So you see that is the big box, which is called active. Actually this is the example of receiving a call. So here we have the ideal state, and off hook, it means that you have to play the dial tone. So only if you are the valid subscriber. So it means that you have put the condition here. So if you are the valid subscriber, that is the condition. If you off hook, the dial tone will be obviously there, should be there. If it is not there, it means either you are not the valid subscriber, or maybe that machine has certain issues. So if you have a valid subscriber, off hook, that dial tone should be there. So you come into a state which is the bigger box here, which is called the active state. You see here, active. So this active is my super state, and all these talking, connecting, dialing, playing dial tone, all these are stated as substates. So as soon as that dial tone is there, that playing dial tone, then you are dialing, it means you change the state. Now you are dialing, it means you are typing the digits. Then if it is complete, the number is complete, then you are connected. Again, it's a different state where you have the connection tone, and once that connection is established, then you are able to talk. So all these activities can be done only in an active state. So therefore this is represented as nested states. So here you can see two transition. As soon as that transition is completed, that discussion is completed, the receiver can be there on hook, and if it is on hook, that the phone will come again in the ideal state as well. State independent versus state dependent. There are two concepts as well. One is called state independent, where we can say the type of object that always respond the same way to an event. Because it is state independent, this is modeless, meaning that whatever the event is, the state will remain the same. The state will not respond to those events. And whenever we are talking about state depending, which is called, in the bracket you can see, is a model. This is not MODEL, this is model, which comes from the word modality, and you also know about model logic as well. So where we need to capture the situations. So obviously when it is state dependent, it is based on certain situations. So type an object that reacts differently. It means the object reacts differently in different situations. So type of object that reacts differently to events depending on its states or mode. So therefore it is state dependent. So we are more actually focused on state dependent, not on the state independent. So UML state machine diagrams for modeling state dependent objects with complex behavior or model legal sequence of an operation, and this is extremely helpful in design, which we'll see later on. Modeling state dependent objects, where we are interested about complex reactive objects. What are those complex reactive objects? Maybe the physical devices controlled by a software. Let's suppose we are talking about physical devices having an embedded software, and that is being controlled by a software, whether it might be a car, it might be a washing machine, it might be an electric oven, any other device which is being used, physical device, and that is being used, obviously that is being controlled by a software. So that is considered as complex reactive object, because that has to receive the input from their environment, and according to that input they have to respond, means in a different manner wherever it is required. For example, you might have the cooling system, and that cooling system has to respond as according to the temperatures. Transactions and related business objects. So transactions are also complex objects. Why? Because transactions are coupled with various instructions. There might be read instructions, write instructions, update instructions. So transaction is actually coupled with various instructions, so therefore it's a complex reactive object. So how those transactions will happen, and when that transaction will be concluded, and in where the transaction cannot be completed, and other business objects as well. Protocols and legal sequence can also be represented in a state model. For example, the communication protocols. So we need to establish a communication between machines, and for that purpose we need a protocol, and that protocol actually matters, because only then that communication may occur, or those transition might occur. If that protocol is not there, those transition cannot be captured. So similarly, it can be represented as UI page, user interface page, window flow. Whoever are designing user interfaces, they know that how they categorize various user interfaces, and how they link user interfaces from one another, and you also design the flow controllers based on certain logic. So all these aspects are easily depicted using the state dependent objects. Now we can see few examples just to understand the concept. This example about a sale, and you can see that transition is started from somewhere, from any point. You can see that starting point over here. That is the syntax of a state model as well. The states are represented as you see in these rounded rectangles, and the state is what? That is, we're talking capturing the sale, waiting for sale. It means that is the ideal state. And let's assume a new sale is being initiated, and whenever the new sale is being initiated, okay, we need to know about items 1, 2, 3, 4, how many items are there. So we need to have items, and when those items are being recorded, then waiting for payment. It means your order will be generated, and when your order will be generated, you have been asked to pick an option whether you go for a cash payment. If you go for the cash payment, you enter here, and obviously you get the product, and your transaction is completed. Or either you go for a credit card payment or a check payment. So in both cases, you need to authorize by a certain agency, maybe a bank or credit agency, and when they authorize the payment, that authorization will be sent to the waiting for sale state, and once it is received, that transaction is completed. You might add certain details into it. This is just a simple diagram, but you might add various conditions into it, various controls into it, and you can make it more detailed version of the diagram. Here there is another example of an ATM, and you can see starting with initial condition, that is reading a card. Okay, let's suppose it is an invalid card. So it means there is a condition. That condition is that whether the card is valid. If validity is there, then ejecting the card straight away. Then there will be no other execution. And if it is read successfully, then it is asked to read the pin. And again, if the pin is invalid, it is obviously ejected. If it is a valid input choosing the transaction, you have been asked that choose a certain transaction which you can do, or the functions you might perform, and all those functions, if you remember, we have discussed in the requirement lecture. There we talk about use cases. All those use cases are there. Find out those one of the transaction. Maybe you are looking for a cash withdrawal, so you can proceed with the transaction choosing, for example, the cash withdrawal. Perform your transaction, or you finish, or after performing the transaction, you may choose for another transaction as well. And at the same time, at the choosing transaction, you might realize that I'll not go for any transaction. So you or you want to cancel the transaction. So you cancel the transaction and you eject the card. So you see that various transitions have been captured, and that is the end of the transaction, which is being represented here with this symbol. So this is another good example of a state transition. Another example here, which is a bit complex, it's about surveillance system. There we have various surveillance system nowadays, CCTV cameras which are there, and we need to capture images. So here you can see it's a bit complex one where we have certain conditions as well, multiple conditions as well. You can see the ideal state from here, and we start from here with the ideal state, and then you see that is the starter. And when you start it, it is initializing and in the initializing mode, and from there you can go and to a new state which is called an operating state, or from the initialization you might go to the diagnosis as one. Maybe you are looking for the system working, so if system is not working properly, you can diagnose it. Otherwise you can go directly to the operating as well, or you can either go from the system diagnosis to the operating as well. So once it is operating, then it means it may be shut down. That shutdown might happen maybe based on a time-based event, as we have discussed earlier on. A certain time the shutdown will be there, or it can be forced shutdown, or that shutdown may happen on the basis of a certain request. So we might have different responses from here. On the basis of this, that operation might be done, and if shutting down is there, then is okay, the response is okay, then the shutdowning of cameras is there, and there we can have a turn off state as well. So that is a good example of a surveillance system. And with this I just conclude my lecture. Thank you so much for listening me, and definitely wait for the next presentation which is coming soon. Looking forward for your positive feedback. And this is my YouTube handle, and thank you so much.